Okay, welcome back, and in this video we're going to talk about a comparison theorem. Okay, so there are many cases where it's not very easy or very difficult to integrate or to evaluate an integral or impossible. And so in these cases, how do we find an answer? Well, sometimes you can't find an answer particularly as far as a value, but if we want to determine whether it converges or diverges, we can at least find out, we can at least decide or determine where that is by comparing it to another function or another integral that is carefully chosen that we can use to compare with the original one. Okay, so what do I mean by that? Well, let's use this as an example. So here, let's say I have two continuous functions, f of x and g of x, and f of x is less than or equal to g of x for all x greater than or equal to a, and of course both of them are non-negative. Okay, and so for example, it might look something like this. Okay, just to be an example. Okay, so we have g of x over here. Now we can look at the areas, so again, if we're talking about integration, we can look at the areas and compare the two areas under each curve over the interval, let's say from a to some value t. Right? And so we can look at this interval and see, okay, as t goes to infinity, how are these areas behaving? Okay, so if we have an integral like this, right? So let's say we have an integral from a to positive infinity of f of x dx, then if f of x is less than or equal to g of x, then we can also know that the integral of f of x dx is going to be less than or equal to the integral of a to positive infinity of g of x dx. Okay. So how can we use this? Well, we can write these as limits. So we can write this as the limit, right? So we can write this as the limit as t approaches positive infinity of the integral from a to t of f of x dx. Okay, and we could do the same thing with this one too. Okay, now, how does it help us? Well, notice, let's look back at the graph. So let me write both of these. So the limit as t approaches positive infinity Okay, so let's take both of these limits and let's just talk about this, okay? So, what do we know so far? Well, here we've got two continuous functions. They're both non-negative, and f of x is less than or equal to g of x for all x greater than a. So again, we've got this interval, right? So for any x greater than or equal to a, we know this is true, right? And so if this is true, we know that the areas under each curve have to act the same way. So the area under the curve over this interval has to be greater than or equal to the area under this curve, right? Because the graph is over. So that makes sense. So now, we can write both of these integrals as limits. Now what if f of x, what if the limit of this integral as t approaches positive infinity goes off to infinity? In other words, diverges. Okay? So what does that mean? It means that the area under this curve goes to infinity. So that means if this area under the curve goes to infinity, then the area under g of x must also go to infinity. Right? So if the integral of this curve here from a to positive infinity for this example diverges, then the integral for g of x as t goes to infinity over the same interval must also diverge. Okay, so that's one. But what if we look at g of x and we find the limit, this limit as t goes to positive infinity, converges to a particular value, let's say L. If the area under the curve is converging to a particular number, so a finite number, and f of x is underneath that curve, then that would also force the conclusion, right, that f of x must also converge to a particular value that's either equal to or less than L. Okay? And so therein lies the theorem that we're going to discuss next. And that's a comparison theorem. It's a way to compare. Now, we're not going to be able to evaluate convergent functions to get an exact answer. We could probably get an upper bound, right? We can get an upper bound of g of x if it converges. And we would be able to say, okay, the integral of f of x over the same interval would have to converge to something less than that, but that's the best we can do. Okay, so this is more used for determining whether a function diverges or converges rather than getting an actual value. Okay? Okay, so in the next video I'll introduce the theorem and we'll go on.